All right. Hi, everyone, and welcome to this session of Google I/O 2016, Designer and Developer Communication. So we'll be talking about both visual design and motion design with a focus on visual design first. So my name is Shona, and I'm an Android visual designer.
Welcome, everybody. I'm Kirill. I'm a UI interface engineer on the UI Toolkit team on Android.
I'm John Schlemmer. I'm the motion lead on the material design team.
And I'm Mark. I'm a motion engineer on material design.
So, as I mentioned, my name is Shona, and I'm a visual designer on the Android design team. As a designer, I get to have a lot of fun coming up with really cool solutions to tough user experience problems. But as I'm creating those solutions, I also need to be thinking about how our talented engineering team is going to be implementing them. So at Google, for every design that's created, we also create a spec to go with it. Together, we're going to take a close look at what makes a spec successful, the assets that we create to support that spec, and also implementation throughout the process, communication, all of that. So let's get started with specs. A spec, or a specification, is a common way for designers to document the exact dimensions, distances, colors of objects and text within the design. But when we say that a designer hands off a spec, we don't mean that they get to wipe their hands clean as soon as it hits engineering. Implementation of a spec is a conversation that exists between design and engineering, and it ensures that we're tweaking and maneuvering to make the most out of the Android platform. To make a spec, designers need to understand some basics about the Android platform first. First of all, there are a ton of screen sizes that we need to account for. Fortunately, we don't need to make unique designs for every one of these screen sizes. That might drive us a little bit crazy. Instead, we can rely on density-independent pixels, or DIPs, to ensure that we can specify one design that will work across a variety of screen sizes. DIPs are flexible units that scale to uniform dimensions across these screens. Here's an example that shows a floating action button across a variety of screens.
I've been doing Android development for over 6 years, for a little bit over 6 years, and I think the most important part for me to remember, and I hope you also remember, that Android ecosystem is this continuum of screen sizes, screen densities, screen resolutions, aspect ratios, and pretty much every hardware aspect that you can think of, there's a variety, there's this continuum. Much like the world of web development, web design in the last 20, 25 years, that doesn't operate on a fixed size of 800 by 600 pixels, the same applies to the world of Android design and Android development. You don't design for the particular screen that you have in your hand just because you love that specific form factor, be it a 4-inch, 5-inch, or maybe a 10-inch tablet. Instead, the layout solution, the layout spec, the way you represent the information in your particular application, in your particular flow, needs to adapt to reflow to the amount of screen space that you have. Instead of, as you can see here on the left, where you don't have a lot of screen estate on a smaller phone, and you go to this vertical list with smaller images, and then as you get a bigger canvas, tablet-size canvas, desktop-size canvas, you can go to a multi-grid, multi-column grid with larger images. And that's just one example of how the representation of your content adapts, reflows, responds to this larger canvas. In the world of web design, it's called responsive design and breakpoints, where the layout, the presentation responds to the changes in the size of your browser window. And breakpoint is that part where you say, OK, now my screen is sufficiently larger to switch to a different way of representing this information. In the world of Android up until now, we chose to call it adaptive design, mostly because you don't really resize an Android application window. It kind of goes full screen, apart from the status bar and navigation bar. This is changing in Android N, where we are introducing the split screen functionality for phones as well as for tablets, where you don't know which part of the screen your app is going to occupy. And it becomes ever more important for your design solution, for your implementation solution, to scale gracefully to that space on the screen.
So one aspect of the continuum that Kirill is talking about is screen density. Dips are our primary way of approaching different screen densities. So let's talk about how best to leverage them. To design using dips, for phones in portrait mode, we use artboards that are rendered at MDPI. So when I say artboards, I'm talking about in Illustrator. And this is with a screen size of 360 by 640. Of course, we still need to create additional designs for tablet layouts, desktop, other form factors, but for the purposes of this session, we'll be focusing on a phone in portrait mode. When we're ready to export these screens, we can do so at 1.5, 2, 3, and 4x to create mockups that are appropriate for different device densities. So in this example, I have created a mock at 360 by 640, which is MDPI, and then I've exported it at 3x to create a screen that is XX HDPI sized. That means that when I put the mock on my phone, it'll show up very crisp and clear, just like it will in reality when it's implemented. There are a few reasons why we work at MDPI from the beginning instead of at a larger density. Firstly, working at MDPI ensures that users on smaller or lower density screens will still be able to read all the text and tap on appropriately sized buttons. Secondly, it's easy to export mocks and assets at higher resolutions after they're designed at MDPI. It's much harder to reduce resolution and still count on your designs being crisp and clean. So in this example, we've taken a larger asset and scaled it down, and you can see that the edges are blurry. Thirdly, when you're working on a 100 artboard file in Illustrator, and each of those artboards is 1080 by 1920, even vector artwork can get pretty sluggish. So instead, we keep those files manageable by working at a smaller resolution first.
So as Sean already mentioned, device-independent pixels, or DIPs, are one of the most basic and one of the most important units or concepts that we have in the world of Android. It allows you to abstract away the physical resolution of the screen and operate on just the right level, at just the right units. I remember I joined the Android team in 2009, just before Nexus 1 was announced, and that was kind of like top-of-the-line HDPI screen. Back then, we had LDPI, MDPI, and HDPI, and now we have XX, XXX, and who knows what will happen in the next 5 years. I don't know. No comment. And it becomes ever more important to remember that you don't operate in pixels. Instead, you operate in DIPs. So every mock that you get from your designers needs to be implemented, all the margins, all the sizes, all the paddings in DIPs, unless you are absolutely sure that you want to use pixels for something like hairline separators. But even those tend to disappear on XX, XXX HDPI screens. So that might not be the best idea. The only exception to using DIPs everywhere is text. For text, we should be using scale-independent pixels, or SP, not SIP, SP. The only difference between DIPs and SPs is that in addition to abstracting away the physical resolution of the screen, user is also able to go into the global device settings and bump up globally, bump up or bump down globally the text size across all the apps. And we should respect that across the entire system. So in your implementation, everything should be in SP units. Finally, everything that can be interacted with on your screen, no matter how big or how small the screen itself is, should be at least 48 by 48 DIPs. And unlike maybe some parts of material design guidelines, this is not a guideline. This should be a very hard requirement that you should not budge from. So as you can see here, example of maybe a smaller asset that you get from your designer, the search icon, which might be 24 by 24 DIPs. But still, when you put it in your actual XML file, however you operate at that level, it might be in a visual designer, it might be hand coding, you should make sure that the actual tappable area around that icon is 48 by 48 DIPs, which you can do with paddings, you can do it with margins, or you can go back to your designer and say, well, actually, the easiest for us would be to cut that asset at 48 by 48 instead of 24 by 24.
As Carol mentioned, typography is spec'd using SPs, scale-independent pixels. Unlike dips, these scale based not only on the user's screen density, but also on their font preferences. So if the user has large text mode turned on for improved accessibility, then we can ensure that your app will observe this and respect it. Now that we've gone over the units of measure for typography, let's take a look at a concrete example. This is an example of a type spec. So you can see that we have indicated font, color, size, and opacity. So these are all key pieces of information to communicate to engineering. However, there is one large piece that's missing. That is text placement with regard to other elements on the screen. So in the material spec, they do a great job of making sure that we have information about how to align text to key lines, and it talks about line spacing between lines of text. However, there are times at which designers will need to spec text placement that aren't necessarily covered in the material design spec. And in those cases, it can be a little bit difficult. This is because design applications like Photoshop, Illustrator, and Sketch all treat text bounding boxes a little bit differently. They tend to add their own padding a little bit at a time, and there's some variety in between them. So for this reason, it can be misleading to try to use text bounding boxes to place text within a design. Instead of using the bounding boxes, we recommend that you use text baselines. By measuring from the top of a container to the first baseline in the block of text, and then from the last baseline in the same block of text to the bottom of the container, we can accurately place the text within the container.
So baseline, at least in Latin scripts, is where kind of the bulk of the text resides, is kind of this virtual line. This is not true for all the scripts out there. Some index scripts that have a little bit more vertical variety, the baseline is slightly below what we would usually consider in like if you come from the world of Latin scripts, what we would usually consider where the bulk of the text resides. We have the ascender line and the descender line, which again for Latin scripts, that is kind of like the true bounding box of the text. But if you go beyond the world of Latin scripts and go global, there are absolutely scripts out there that have some parts of their glyphs, some parts of their characters going above the ascender line, below the descender line, or both. And these are just a few examples from around the world of scripts that have a little bit more vertical variety in their rhythm. And some developers that want to have a little bit more precise control over placement and alignment of text choose to use the Android include font padding attribute and set it to false. That works great for Latin scripts. You have that precise control, but you will discover that it starts cutting off those top and bottom parts of the glyphs under index scripts and under a wide variety of non-Latin scripts. So instead of using that attribute, which is heavily discouraged, instead get the font matrix object from your text view. Then you can query different attributes, different fields on that font matrix to get the ascender, where the ascender line, where the descender line is, and a couple of other parameters, attributes, and then call set line spacing API in your text view to increase or decrease the line spacing based on the particular requirement from your design. Finally, if you want to tweak the vertical rhythm in between text views that are stacked vertically, you can set top and bottom padding on the text view once again based on your design and based on the specific matrix of the font that is currently being dynamically used under the particular locale.
So as you can tell, typography can be a tricky subject. However, when it's done well, it can add a lot of polish to your app. Also remember, whenever possible, preview your designs on an actual device. So put the mock-up on the device. That way you can tell whether your text is readable. There's really nothing like actually seeing the screens on a device to figure out when your designs are working or not. Let's shift gears and talk about shipping some assets. Earlier, we talked about the importance of working at MDPI when you're working on the overall design. This is still true when working on assets. When making icons, 9 patches, and other graphical elements, we still want to be working at MDPI, like in this example, which has an asset from material design at 24 by 24. By ensuring that the asset is crisp and clean at the small size, when we scale it up by 2 or 3 or 4x, we can ensure that it remains just as crisp at the larger sizes. Going the other direction, moving from large to small, it's easy to run into icons that have blurry edges and poor definition as they're scaled down. This is because vector points that fell on whole pixels at the large size can start to fall on partial pixels when scaled down. Here's an example of an icon that started large and got shrunk down to a smaller size. You can see that it has blurry edges. Remember that since we're talking about Android, we need to ship assets at a variety of sizes to suit all screen densities. At Google, we typically use PNGs for this because they handle transparency very well while still maintaining small file sizes. However, one of the great new features that we recently introduced is backwards compatibility for handling vector assets. Previously, vector assets were only available to Android 5.0 and beyond. With the new availability of vector drawables in older versions of Android, now assets like this icon can be shipped as a single vector asset and scaled dynamically at runtime. This is absolutely fantastic for APK sizes because the size of a vector asset is far smaller than the aggregate size of all the PNG assets that one would need for all the screen densities. But remember, designers, your vector assets will need to be perfectly snapped to the pixel grid in order to appear crisp and clean when they are rendered.
So going back to this variety, this continuum of screen densities, once again, when I started, it was HDPI was the top, and now we have, let's say we're not shipping LDPI assets anymore anywhere, but you still have lower spec, lower end devices at MDPI. So if you go MDPI, HDPI, single, double, triple X, and once again, who knows what will happen in the future, those PNG sizes start adding up pretty quickly. And vector assets are a great way to cut down on that extra size introduced by the assets, by these PNG assets, to your overall APK binary size. And this backwards compatibility support for vector drawables that was added as part of the AppCompat support library, when we switch that support library itself to use vector assets for a variety of like search box icons in a couple of other places, the overall binary size of that module of that support library dropped by 9%. And 9%, if you multiply it by however many devices your app happens to target or you hope to have, that's a lot of bytes, megabytes, hopefully gigabytes, terabytes. This is how you go about enabling backwards compatible support for vector assets. If your app is targeting pre-Lollipop devices, devices that ship with pre-Android 5.0 release, the same way you have your vector drawable in your resources folder, you enable the support for vector drawables in your Gradle file, and then automatically your image view that is under the hood automatically converted to use the AppCompat's version of the image view has this built-in support for vector drawables as its sources. If you still use PNG assets, there's great news for apps that want to tint or colorize a certain asset or more than one asset based on the specific colors that you are using. Play Store is a great example that is using this. In Play Store, we have this kind of color language for different parts of our media offerings. We have light blue for books, darker red for movies, orange for music, and so on. So instead of shipping 5 or 6 sets of assets that have the same shape but are colored or tinted differently, instead, we can now ship only one base set of assets, PNG assets, that are just white color, and then colorize them at runtime, tint them at runtime by wrapping the original drawable and then calling these APIs to set tint or set tint mode. And this works great, by the way, with the overall iconography language of material design that has simple shapes and that has single color, and that lends itself very well to representing those icons in vector format.
Okay, now that we've got a robust spec and a set of assets to work with, design's work wraps up and implementation begins, right? No, not the case. Remember, we don't hand off. Instead, we consider design and implementation to be part of a larger conversation. Since we're all working towards great experiences for our users, we make sure that Eng and design are collaborating from the beginning so that when we ship a product, it's both beautiful and functional.
So I might be dating myself a little bit. I remember the old days of waterfall approach to developing, designing applications. Those were bad days. So basically, designers would do their own thing as one big iteration. You wouldn't even call it iteration, you would call it a phase. And then they hand over the entire spec to you as a developer. And then you go away and you work on however many weeks or months that happen to be needed. And then this is done. This is not how it should be going, especially in the world where we target this variety of screen densities, screen aspect ratio, screen resolutions again. You should start with something quick, low-fidelity mocks that you implement and put on this piece of glass in your hand so that you can see what works and what doesn't work. It doesn't have to work with the real backend. It doesn't have to work with real images. But it definitely informs your next iteration much better than just looking at this pixel-perfect mock of your phone screen size, phone screen, that is on this gigantic 30-inch monitor that designers love. It's not the same level of kind of feedback that you get from having something on your device. And then your next iteration, you grow progressively from low fidelity to higher fidelity mocks. At every step, you know that you are making these informed decisions. I call this here corner cases, but they are anything but corner. You need to think what happens when your implementation, when your app, when your flow lives in the real world. And the real world is full of 2G or 3G connections when you wait for multiple seconds to see those information bits that are not yet available as they are loading from the mobile network. You live in the world where people are on metered connections and so on. So you need to think about what happens during that loading phase from the design perspective, how the design scales to those intermediary states, and how, from the implementation perspective, you address those empty states, intermediary loading states. As far as an empty state, something like inbox 0, people love inbox 0. So what happens when you don't have anything in that inbox? What happens when you just join the new social network and you don't have anything in your stream? Instead of discouraging the user with this empty canvas, instead you can encourage him or her with something a little bit more human, a little bit more friendly, like seen here in the example on the left. In the example on the right, you can see what we call tinting or colorization of certain pieces of your UI based on predominant, vibrant, other colors from this hero graphic. But what happens if this hero graphic is loaded from the network, when you can't preload all possible albums, all possible movies, and whatever you happen to have in your app from the very beginning? You need to think about, from the design perspective and from the implementation perspective, what do you do with those elements, with that fab, with that progress indicator where you can already play the song, but you still don't have the cover art for it. The same goes for localizations, which can go a little bit longer in German or Swedish, or in scripts such as Korean or Chinese, they're a little bit taller. So your design needs to be aware of what happens when you are not running only on your particular screen under English US.
So keep in mind that our designs are often pushing at the boundaries of what devices are capable of handling. There will always be technical limitations to what can be reasonably implemented. Navigating those limitations is the responsibility of both designers and engineers. Like I mentioned before, implementation is a conversation, and it's important to get input from the entire team. Everyone's working towards the same goal of creating awesome experiences. It's when we collaborate across design and engineering that we end up reaching the most amazing solutions. And now we'll hand it over to John, here to talk about motion design.
So thanks, Shona, Kirill. I'm John, and I'm here to talk to you about motion. So motion implementation can be pretty different than visual design implementation, but it's still a really important piece of the puzzle. So the material design team just launched some brand new extensive animation guidelines that can be seen at design.google.com. And we're definitely raising the bar on animations this time. We have objects moving in curved paths instead of in straight lines to give the movement a little bit of a more natural feeling and less of a robotic feeling. We have the width and height of surfaces transforming asymmetrically to kind of match this curve movement too. We have content within these asymmetrically expanding surfaces that follow these curved paths. And the movement of both need to stay consistent and contained. There are definitely right and wrong ways to animate for sure. And that's what these new animation guidelines can help you. But that's only half the battle. At the end of the day, this needs to get implemented. And all too often, I see animations being pretty different from what the original design in After Effects look like and the final result in the app. And this is rarely because of the skill level of either the designer or the engineer. Sometimes it's around the designer making an animation in After Effects that isn't quite possible to do on Android or iOS. But most of the time, it's actually about how that motion is communicated, or not communicated, to the engineer. A designer can't just hand over an exported MP4 file and wipe their hands clean, right? There are so many subtleties that go into proper motion. And there's no way anybody else that sees it, designer or engineer, will be able to quickly pick up on all these subtle details. It's honestly just not nice to make an engineer scrub through a video frame by frame to try to point out and guess what's going on. The communication absolutely needs to continue from that initial export, and proper communication with that engineer during that and as he or she is building it is required to help move it forward and see if it's even feasible on the platform in the first place. So let's take a look at this animation in Google Calendar. It's probably the most seen animation in the app, so it's pretty important we get it right. We tap on an event, and we go into the event view. We go back, and it collapses again. It's pretty simple, right? Just expands and collapses. But there's so many details here, so let's take a look at them. The width of the card actually transforms at a slightly offset rate than the height of the card. The content inside of the card moves in a strategic way to give you the illusion that it lines up with that separate title field in the header. The image inside of the collapsed event is actually a partial reveal of the new view, and it lines up with it. The exact timing of when that old content leaves the view and the new content comes into the view is also really important to prevent any flashing or disturbances in the loading. The edit fab is actually attached to the intersection of the header image and the white content below it. And the RSVP card, in some cases, slides in from the bottom where it's applicable. And that's just opening an event. What about closing it? It's also not the same animation reversed. And this is a really common mistake I see a lot of designers and engineers make. Simply reversing this animation is not really enough to convey the subtleties of motion that were introduced when you were expanding it. The path may be a little different, and the time at which the objects leave the screen are different from when they enter the screen. And then you have to think about which easing curve to use for all of this. The motion designer might know these curves according to their software, but it might mean completely different things to the engineer. An outgoing easing value in After Effects is actually referred to an ease-in value in other software and languages, while an incoming easing value in After Effects is actually referred to an ease-out in other languages and software. So that's already pretty confusing. To make it worse, there's a right and wrong time to use each one of those. And mixing those up can have pretty dramatic effects, too. There's a lot of communication in what would be a seemingly simple expand and collapse animation. And I really wanted to go over these details with everybody just to show both the designers and engineers everything that goes into it. Designers, you should absolutely be considering every detail when you're making a transition like this. And I highly recommend checking out the new animation guidelines in the material resources. Engineers, you should be aware that designers are thinking about this. There are these little things that go into the animation. And you have every right to be mad at them if all you get is an MP4 file emailed to you with no further explanation. So how do we at Google actually communicate this motion design? Every motion designer has their own tricks, but I'd like to go over what I found to be the most useful way to get detailed information to the engineer, just so they have access to the right delays and easing curves and values right from the beginning. We'll be looking at this animation in Inbox that you see the most, opening an email. And here to slower so you can actually see what's going on. I showed this before, but this is what I have in After Effects. It's a pretty complex timeline with a bunch of hidden information throughout the interface. Somebody not familiar with After Effects would probably have no idea what they're looking at. So giving an engineer an After Effects file probably isn't the way to go either. What I do, along with a lot of other motion designers here, is I create an animation graph a little like this one. This is the animation graph I made for the inbox expanding animation that Mark and I actually worked on. Yes, it's still a timeline, but it's so much more digestible in this form. Instead of in frames, it's measured in milliseconds, which is what engineers actually need to know. Each line on the graph is actually an animated property of an on-screen element. So opacity, scaling, position, X and Y, all of that is located next to the name of the elements that's transitioning. The x-axis gives you an idea of when that transition actually starts and for how long it takes place. Easing curves are also noted here. So since material design uses a pretty common set of 4 different easing curves, naming them here and identifying them here can let the engineer cross-reference them with the animation guidelines. And there it'll actually give you the exact interpolator or cubic Bezier curve for that value. It's a little more work for the designer up front to create something like this for an engineer, but I promise you, in the end, it'll take so much less time than trying to figure out where an animation went wrong and tweaking from an already incorrect one. This has helped me get animations implemented with accuracy from the very beginning. And while handing off a video with an animation graph is way better than just a video, the communication still shouldn't stop. A designer might have a slightly tweaked design they need to communicate, or an engineer might have a roadblock that they run into as they're building it. There's always going to be edge cases to work through, as Kirill mentioned too. There's always going to be them. But I won't get too far into that. I want to let Mark Way talk about his experiences working with designers and motion designers to implement this motion.
Thanks, John. I'm Mark, and I'm a software engineer focused on motion. I've worked with John on the Inbox app and now on material design. Front-end engineers often strive for pixel perfection. Motion engineers strive for frame perfection. I'm here to talk to you today about the pain points I've encountered while trying to achieve this goal. As John mentioned, engineers should not be expected to implement motion from only an After Effects video. I've often found myself scrubbing through a video frame by frame, trying to pry apart complex motion. Even worse, sometimes there isn't even a video, and I'm asked to implement something on Android by seeing how it was done on iOS. Have you ever tried to figure out? Thank you. Have you ever tried to figure out an easing curve by inspecting the frames? It's not a very good use of time. But fundamentally, a video only shows a slice of the motion spec for a very specific set of initial conditions. Engineers are always interested in a more general case, so a richer motion spec is necessary. This is where the animation graph comes into play. But sometimes, even the best motion designers and engineers don't speak the same language. Here are some caveats to look out for. And keep in mind, these are all actual examples that I found in apps both inside and outside Google. Let's take a look at this expanding card. The animation graph might have a component for width expansion and height expansion. But how exactly does a card expand? Should you scale it, or should you mask it? The end results are completely different. Try to use specific language like scale and mask in your motion spec. Avoid generic terms like expand. Things get complicated when rounded corners are involved. For material design, you may not want to actually animate the radius of a rounded corner. Instead, think about breaking it down into overlapping masks. It helps to include a wireframe video showing the masks in your motion spec. This is especially true for more complex motion with multiple components. Text scaling is really hard to get right. Keep in mind that an engineer may be constrained by her platform. For example, When you change the font size of an Android text view, you cause not only an invalidation of that view, but also a relayout. This may cause performance issues. A common workaround is to just scale the entire view, or you could draw the text manually onto the canvas. The collapsing toolbar in the Android design library, as shown, is a good example of manually drawing the text to allow its font size to change smoothly. As engineers know, it's the edge cases that are the hardest to deal with. What if the text reflows to multi-line? What if the style changes to italics or bold? Include text scaling behavior in your motion spec. Keep edge cases in mind and know that many times a simple crossfade is acceptable. And on the topic of performance, it's something the designer should also be aware of. On many platforms, animating the alpha of a layer is actually quite expensive. For example, on Android, you must be careful when animating the alpha of a container, like the toolbar in this video. Since its contents are being translated independently, they must be redrawn on every frame. This becomes a problem when the container's alpha is being animated and may again result in performance issues. In this case, the engineer may choose to apply the alpha to each individual icon rather than the entire container. If the designer is aware of these limitations, the motion spec can be designed around them. Motion specs are usually concerned with going from state A to state B, taking a certain duration. But in the real world, user behavior is not so clear-cut. They may want to cancel out during an animation or tap on an item that's still coming into view. And there's nothing a user hates more than having to wait for a transition to finish before continuing to interact with the UI. It's usually been left up to the engineer to decide whether animations can be interrupted. Going down the easy path often means that UI elements become frozen while an animation is in progress. Instead, consider clearly defining in your motion spec the behavior of interruptions. I'll leave you with a personal anecdote. I recently implemented the transition from a floating action button to a sheet. What you're seeing is a sheet with a circular mask applied to it to look like the fab. The sheet starts partially off-screen and translates vertically until it's fully on-screen. At the same time, the circular mask expands from the size of the fab. The interesting thing is that the end value of the circular mask expansion is defined as fully covering the visible area of the sheet. Now, some of you may have realized that this is actually a moving target. As the sheet translates, the visible area grows. So first, I calculate, at this exact time, how much of the card will be visible? And then I use that to determine the end value that the circular mask expansion should be. This seems to work, but actually, there's something wrong. Now, you'll notice that everything in the video actually looks fine. Unlike working with static UI, you might not find any obvious visual glitches when motion goes wrong. But when I slowed down my animation, I realized that the sheet was fully revealed 25 milliseconds before it was intended to. The red highlight you see marks the beginning of that moment. Now, 25 milliseconds may not sound like much, but that means that instead of a circular expansion happening over 6 frames, it now happens over a much more quicker paced 4 frames. When played back at full speed, it felt ever so slightly off. So I triple-checked all my numbers, but everything looked fine. While I was struggling to find an explanation, I hit a sudden inspiration, and I scribbled this graph down in my notebook. The longer line describes how the vertical translation of the sheet shows more area over time. The shorter line describes how the circular mask expansion covers more area over time. The curvature of the two lines are caused by the standard easing curve applied to both. The last intersection between these two lines show where we want the two areas to coincide, satisfying the motion spec. But we can clearly see that there was an unintended intersection. That represents an earlier time when the circular mask already covers the entire card, which the user perceives as a shorter duration. My motion designer did not encounter this issue in After Effects, but I did in my implementation. Why is that? It's because there exists a certain set of initial conditions, the size of the sheet, the size of the fab, the distance between them and the edges of the screen, that resulted in this particular situation. In the end, I communicated this to my motion designer, and we decided to change the easing curve of the circular mask to avoid this. Is this guaranteed to work for the entire set of possible initial conditions? It's hard to say. Whenever you have animations that are defined to be dependent on one another, you may run into problems like this, and they will be difficult to notice and difficult to fix. Great. I was able to resolve this issue with a simple easing curve change. But this just shows the importance of communication between designer and developer. Some motion specs are ambiguous. Others are difficult due to platform limitations. But a few are just plain impossible because of reality. Having an open communication will ensure that your intent behind the motion spec is properly implemented. And if you keep these caveats in mind, you and your engineer can start to speak the same language.
All right, so that wraps up our session. If you're interested in learning more, please check out some of the links on the slide or join us online for continuing the conversation. Thank you so much for attending.